The next thing I want us to talk about is trees. So trees are a type of graph. They're a very specific type of graph. And sometimes in graph theory, we want to restrict our focus on a particular type of graph because there are so many out there. And so we're going to spend this section focusing on T-graphs. These should be a little bit intuitive. So a tree is a connected graph containing no cycles. Remember that a cycle is a path that starts and stops at the same vertex. So, for example, I could have this tree and as you can see, this is a cyclic. That means it has no cycles. It would have a cycle, however, if I did this, right? Because then there is a path where I could start here, let's call this vertex A, and follow around to my path. But we don't want to do that, so I'm going to erase that, right? So we have this looking like a tree. Very exciting, okay? So this is a tree. A forest is a graph containing no cycles, okay? So it's just like a tree. But notice we don't mention the part that it's connected anymore. Like, we don't care that it's connected. A tree is a connected graph. A forest is not a connected graph. So, for example, this could be a forest. It contains two trees, right? Forests are made up of trees. So we have a proposition. The first proposition is that every graph T is a tree, and if and only if, between every pair of distinct vertices in T, there is a unique path. The word here is path. There is a unique path. It's important to know that adding a cycle would ruin this proposition, and I'll show you why. So let's go ahead and draw the tree we had on the last side. He's kind of a funny looking tree, but I like him. He gets the point across. Okay, so let's try and find a path between here and here. As you can see, there's only one path I could take. If this was not a tree and I added another cycle, so let's draw this again. And let's say I add a path here and I want to find a path from here to here. I could go this way or I could go this way. There's not a unique path. So it's important to note that you can't add a cycle. It would ruin the proposition. It's also nice to know that every tree is a bipartite graph. Fun fact. Here are some other properties of tree. A corollary F is that a graph is a forest if and only if between every pair of vertices there is at most one path, i.e. it's a tree. Another proposition is that any tree with at least two vertices has at least two vertices of degree 1. Let's take a look at that. So if I was to sketch a picture of a tree, here's a tree with two vertices. Kind of boring, I know. It's connected. It's a tree. This is degree 1 because it only has one edge coming into it, and this is degree 1 as well, right? If I want to make a degree 3 tree, well, this is degree 1, this is degree 1, right? So any tree with at least two vertices always has at least two vertices of degree 1. Let's let T be a tree with vertices and edges, then E equals V minus 1. So here I have 3V, so I've got two edges, as you can see. I've got 1, 2. Here I have 2V, I've got one edge. Let's take a look at the example we've been looking at this entire time, my cool tree right here. So I have 1, 2, 3, 4, 5, 6, 7, 8. 8 vertices. And I have 1, 2, 3, 4, 5, 6, 7 edges. And this proposition is going to hold true no matter how large your tree gets. There is a proof in the book. Next, I want to talk about rooted trees. This is something we do in class. In like college algebra, an example of this would be to do a factor tree, except then like what we're trying to factor is the root. Friendly, fun connection to college algebra. So a tree in which a vertex is designated as the root is a rooted tree. Okay, then every other vertex can be characterized by its position to the root. So let me go ahead and draw a rooted tree. We're very excited, I know, with very little room. Let's use green because it is a tree after all. Okay, so I've got tree A, B, C, D, E, F, that's an F, G, H. Okay. So if two vertices are adjacent, then one of them is the parent as the other in child. So the parent is the vertex closer to the root. So here we see B is the parent of D, and D is the child of B. All non-root vertices have exactly one parent, right? It's not possible for E to have any one more parent, right? If it had another parent, we would have like connected a line here. Then it wouldn't be a tree because it's got a complete cycle. So let me erase that because that's a no. Okay. The child of a child of the vertex is called the grandchild of the vertex. So H down here would be the child of G, but the grandchild of C. So C is the grandparent, right? It's like making a family tree. C is the grandparent of H, and H is the grandchild of C. We could also say that a vertex is the descendant of another vertex, provided U is a vertex on the path from V to the root. So we can say D is a descendant of B because D is on the path from D to the root. So B is an ancestor of D, and D is a descendant of B, right? This is all terminology very similar to a family tree. Pairs of vertices, neither of which are descendants of the other, are called cousins or siblings. So in this case, D and E are cousins. Because they're not descendants of each other, and D and C are cousins, but their siblings only have to have the same parent. So here we have E, F, and G are siblings. A spanning tree is a tree that when given a connected graph, G, a spanning tree of G is a subgraph of G that's a tree that includes all vertices of G. So what we're doing is we're getting rid of the edges that connect them in order to make this a tree. And each spanning graph could have multiple trees. So let me show you what this would look like. Okay, so here we have two graphs. I'm going to find two spanning trees. And when we're spanning trees, touch all the vertices. So I could do this spanning tree. I could even do, let's switch to orange, this spanning tree. It's totally up to you.